So today we'll see an algorithm for matrix multiplication. All of us know how to multiply two given matrices. I'll assume both matrices are n by n. So there is a very simple method. Basically, you take a row and multiply with each column. That will give one element in each row. So if you do it for each row for the left hand side of the matrix, then you will get all the elements. That we know already, and that algorithm, if I tell you to write, you will write an order n cube algorithm. There will be basically 3 loops, each going over n. Today first we will see how these n cube operations can be avoided. How the total number of multiplication, n cube multiplications, can be avoided using some divide and conquer technique. So let me first tell you a different method for matrix multiplication. So we are assuming, so this is another algorithm for matrix multiplication. So I am assuming that you are familiar with the usual matrix multiplication algorithm for matrix multiplication. For the convenience, again I assume n is equal to 2 to the power k, is a power of 2. Now suppose we have been given this matrix A and I have been given another matrix, say B, both are n by n. Then the first thing what we do is to divide this matrix into 4 equal parts. Both matrices, we divide this both matrices into 4 equal parts. I am calling this part A11, this is A12, A21, A22. Similarly, this one B11, B12, B21, B22. Mind that each one is n by 2 matrix. So this A11 is a matrix which is n by 2, each one of this. Now suppose we write C is equal to A times B. So we want to compute the elements of C. So let me write C again into this 4 equal parts. So I am going to write C is equal to AB, which is again a n by n matrix, which we are going to divide into 4 equal parts, and we are calling this one as C11, C12, C21, C22. Now applying the usual rule for matrix multiplication, one can see that C11 is basically A11 B11 plus A12 B21. Remember, these are all matrices. So this means a matrix multiplication, but each of dimension n by 2 cross n by 2. So C11 is this. Similarly, C12, you will find this is nothing but A11 B12 plus A12 B22, and C21 is A21 times B11 plus A22 B21. C22 is A21 B12 plus A22 B22. How we are getting this each element? Let me go over this previous slide a little bit, then it will be clear. So we are trying to get C. So C looks like this. Again I divide. So this is here C11, this is C12, C21, C22. So I should be getting this element by multiplying this row by this column. So if you multiply that way, then it is A11 B1 plus A12 B21. So C1 should be A11 B1, A12 B21. exactly that is here. C11 is A11 times B11 plus A12 times B21. Similarly, all the others. Now, if we, so suppose we use this algorithm to compute the elements of the matrices. So, in that case, let us write down the recurrence relation for all the operations we are doing. The number of operations we are doing is that nothing but the number of multiplications and the number of additions. So, if I write that, then Tn suppose is the time to multiply two matrices of dimension n by n. So, in that case I can write Tn is equal to how many multiplications we are doing here. Let me go back again. Actually it is 8 because each Cij requires two multiplications, two matrix multiplication of dimension n by 2 n by 2. So, there are 4 Cij's. So, we have 4 times 2 8. So, there are 8 matrix multiplications each of dimension n by 2 n by 2. So, I can write then the Tn is equal to 8 times Tn over 2 plus, let us go back again, we have this addition here. So, even if we call recursively for this multiplication, we have to do this addition, which is nothing but adding two n by 2 n by 2 matrices, and that will require how many operations of additions? Order of n square, because it is n by 2 times n by 2, which is order of n square. So recurrence relation becomes Tn is equal to 8 times Tn over 2 plus order of n square. So, if you solve this recurrence relation, we know how to solve it. You can unravel it or you can apply Master's theorem. In that case, what you will get, this is nothing but order n to the power log 2 base 8, which is order of n cube. So, in terms of time complexity, we have not saved anything by doing this, because the usual matrix multiplication also takes order of n cube time, multiplying each row by each column. That also takes, each multiplication takes order of n, there are n square such row versus column multiplication. So, that is also n cube, but this has told us that at least we can use divide and conquer paradigm for matrix multiplication. So, only problem is that the number of multiplication is 8 here, and that is causing this to blow up to n cube. But if we can reduce this quantity 8 to any number less than 8, then we will save the time complexity immediately, and that will be our goal now. Now, let us look, let me point out that even if this part is not n square, suppose it is more than n square, in that case suppose it is order of n to the power 3 minus epsilon for some epsilon greater than 0, very small quantity. Even if that it is like that, then this entire recurrence relation will solve still to order of n cube. So, we can have a leverage here. It need not be n square. It can, if it is less than n cube by any small amount, small means in the power, not 3 n cube minus epsilon. It is n to the power 3 minus epsilon to the power. For any small amount, still it will solve to order of n cube. So, now let us see how can we decrease the number of multiplication to 7 instead of 8. Let me write down some sequence of operations. So, I am going to write P1, I will write basically 7 quantities. So, let me write P1 is equal to A11 B12 minus B22. Then P2 I am going to write A11 plus A12 B22. P3 is equal to A21 plus A22 B11. P4 is A22 B21 B11. P5 is A11 plus A22 B11 plus B22. P6 is A12 plus, sorry, this is not plus, minus A22 B21 plus B22. P7 is A11 A21 B11 plus B12. So I have just defined 7 quantities. They are defined over matrix multiplication and additions, but each matrix is of dimension n by 2 n by 2. And if I just see what are these quantities, I am going to write it here. So this is nothing but if you multiply A11 B12 minus A11 B22, you will get. We are just going to verify something. So this one will give you A11 B22 plus A12 B22. This one will give us A21 B11 plus A22 B11. This one will give us A22 B21 minus A22 B11. This one will give us A11 B11 plus A11 B22 plus A22 B11 plus A22 B22. This one will give us A12 B21 plus A12 B22 minus A22 B21 minus A22 B22, and this one will give us A11 B11 plus A11 B12 A21 B11 minus A21 B12. So these are just there is nothing complication is here. It's a very routine task to see what are this P1, P2, P3, P4 up to P7 are. This is just a routine task. So after knowing this, I am going to write some other equations which you can again immediately verify from this. So I am going to write some other equations again. So the equations are C11, I am going to write. So you have to verify that it is exactly so. I am claiming that C11 can be obtained from P5 plus P4 minus P2 plus P6. You have to verify this. You take P5, we know the values of P5, P4, P2, P6. If you do this, you will get C11. You will get C12 if you do P1 plus P2. You will get C21 if you add P3 and P4. Similarly, you will get C22 if you do this P5 plus P1 minus P3 minus P7. So this is telling that all the elements of C 1 1 1 2 2 1 up to 2 2 you can get from PI's up to 7. by these equations, and these equations are only additions. Additions are nice because additions of two matrices will take only order n square time. It is a multiplication of matrices which are costly, which we want to avoid. Okay, so if you verify, this will give you actually A11 B11 plus A12 B21. This one will give you A11 B12 plus A12 B22. This one will give you A21 B11 plus A22 B21, and this one will give you A21 B12 plus A22 B22. So you have got all the elements from PIs. Now let us go back to these previous equations. To form PIs, we have to give a recursive call to matrix multiplication. How many matrix multiplication we are using? There are 7 quantities we have to compute, and each one requires only one matrix multiplication. Here is 1, here is 1, here is 1, 1, 1, 1, 1. So each quantity of PIs requires only one matrix multiplication. There are additions, but as I told you, additions are nice. It's okay. We can have order n square time. We can afford it. So we are using 7 matrix multiplication recursively, and of course there are some additions which is of the order of n square, and we are getting this entire matrix multiplication. So we can write now this recursive algorithm. The complexity I can write now Tn is equal to, can you tell me what is this? 7 times Tn over 2 plus order of n square. And if you solve this, this will give you order of n to the power log 2 base 7. And now we have saved the time. It is not anymore n cube, because n cube is n to the power log 2 base 8. Now it is log 2 base 7. And if you calculate this quantity, it will give something like order n to the power 2.808. So although all these are very routine, the entire algorithm, if you ask me how have you got this, yes, probably by somebody by some trial and error method probably has got it, probably. Okay, but the whole point here is that divide and conquer, if you are clever enough, if you do some tricks, it can save, which seems to be almost unavoidable. Initially it seems that order n cube matrix multiplication is almost unavoidable. We have to multiply n cube quantities, but it's not so. That's the whole point here. It's not whether it is 2.8.0 or 2.9. So the paradigm of divide and conquer is very powerful. We have already seen it in polynomial multiplication, matrix multiplication, in many other algorithms also. So probably when you are given some problem, the first thing probably you should try the divide and conquer. Then you should use probably other paradigms also. But divide and conquer is a very often used paradigm for algorithm design. So this is the matrix multiplication, and this is called the Strassens matrix multiplication. The algorithm which I just told you, I didn't write the pseudo code, but I hope you can write it. So this is called this Strassens matrix multiplication algorithm, and it was found in 1969. Till then, it has improved actually. Now there is an algorithm which we will not cover in this class. That algorithm can do in order n to the power 2.376. So right now there exists an algorithm which can do the matrix multiplication in order n to the power 2.376. So this is very, now you can see 2.3 is quite less than n cube. 2.3 is quite good than n cube. But what is the lower bound known for matrix multiplication is only omega of n square. Nothing else is known till date. Till today, the only thing we know that it will require at least n square time. Nobody knows whether it will require more than that. N square is obvious because we have to compute at least n square elements for the matrix C. So we cannot avoid n square computation. So lower bound is obvious, but nobody has improved the lower bound beyond this. And the upper bound is this. So this is quite close, but still there is a gap. And people go on decreasing this one by little. But the point is, nobody knows what is the optimal value. What should be the right complexity for matrix multiplication? Such a basic problem, we don't know what is the optimal complexity, what is the right complexity. There still lies a gap till today. And let me make one more point, then I will finish this matrix multiplication. When we did this order n to the power 2.8.808 algorithm, there is another why people would devise something probably which is a little bit complicated and it does not achieve that much. Like I would say this Strassens algorithm, it is order n to the power 2.8 and the usual matrix multiplication gives order n cube. So difference is not that much at all. But probably this is a little bit complicated because you have to do recursive calls. And recursive calls has their overheads on the computer. So the system will take up some time for recursive calls because system maintains a recursive stack. And that maintenance and all those things, ultimately probably in the practical sense, it will not improve your time of the code, running the code, if you do this Strassens multiplication. But the point here is that theoretically we would like to know whether n cube can be beaten at all, whether n cube is the barrier. Suppose somebody comes someday and tells that matrix multiplication can be done order n to the power 2.999999 say 1. Still it has a significance in the sense, then at least it is known that n cube is not the barrier. And very likely that 2.99991 is not the right complexity, so probably people will now try to beat it further. That's the implication. So further research will go to beat it down. But if n cube cannot be beaten, people have a doubt now whether n cube is the right complexity. So there is a significance of designing algorithms for this, even if it is not very practical. And actually it will be a very good exercise to see for which value of n, when this Strassens algorithm will perform better than the usual matrix multiplication algorithm. It will perform better. For large value of n, I am sure about it. Because this will take over. Ultimately the overhead will be taken over. But it will be a good exercise if you go and check for which value of n actually this will be better. So with that one I finish this matrix multiplication. We will see some other algorithm in the next lecture.